Hello there, and welcome to the Sleepy Science Story. Close your eyes for a moment and imagine drifting slowly through the quiet darkness of space. Far away from Earth, beyond our sun and beyond everything familiar, there are distant worlds silently circling faint stars. Some glow softly like lanterns in the night. Others are covered in endless storms and swirling clouds. Out here, there is no noise, no rush, only calm, peaceful silence. Tonight, we'll explore these mysterious planets together, gently and slowly as we drift deeper into the universe, discovering how strange, beautiful, and dreamlike these worlds truly are. Take a deep breath and let yourself relax. Let your mind drift as we journey to worlds that defy imagination. Some planets are hotter than stars themselves. Stars are immense furnaces glowing with plasma at millions of degrees, yet certain exoplanets rival them in sheer heat. Consider Kelt 9b, a gas giant scorching at over 7,000 degrees Fahrenheit, hotter than many red dwarf stars. It races around its massive blue star, completing an orbit in just over a day. Tidally locked, one side bakes endlessly, while the other lies in permanent darkness. Its atmosphere streams into space like a comet's tail, and the heat is so extreme that molecules disintegrate and metals vaporize. These ultra-hot Jupiters stretch our understanding of what a planet can be, blurring the line between planet and star. They host short-lived blazing storms and infernos that dissolve as quickly as they form. Some may even be rich in carbon, forming exotic worlds of crystalline diamond. Take 55 Cancri E, a super-Earth twice the size of our planet, where immense pressure beneath the surface could create vast regions of diamond. Not glittering like jewelry, but dense, dark, and extraordinary, a planet shaped by carbon under unimaginable pressure. And then there are planets that orbit not one, but two suns. Like scenes from science fiction, these circumbinary worlds host twin sunsets and celestial choreography unlike anything on Earth. Depending on the distance between their stars, such a planet may orbit both suns together or dance around one, gently influenced by the other's distant gravity. These extraordinary planets reveal how diverse, strange, and awe-inspiring the universe truly is. Imagine a world where sunlight dances in unusual rhythms, casting double shadows and creating seasons unlike anything on Earth. Such rare systems exist, and on these distant planets, the sky may truly welcome two dawns and two dusks, a vision once the realm of fiction, now quietly confirmed by science. Some planets are so alien that even their weather defies imagination. Take HD 189733b, a gas giant larger than Jupiter, orbiting so closely to its star that a year lasts just over 2 days. Its atmosphere blazes at nearly 1,700 degrees Fahrenheit, with winds racing at thousands of miles per hour. Tiny silicate particles float in its blue haze, dust that can condense into rain not of water, but molten glass whipped sideways by furious winds. From afar, it glimmers a soft blue, deceptively calm, yet up close, it is a storm furnace, violent, beautiful, and utterly uninhabitable. Other exoplanets are vast ocean worlds where water stretches thousands of miles deep and no land interrupts the endless seas. Beneath the surface, immense pressure transforms water into exotic forms of ice, denser than anything on Earth. Some may hide rocky cores or warm liquid layers driven by internal heat. Could life exist there? Perhaps. These oceans remind us that nature's creativity reaches far beyond our imagination. Many planets are tidally locked, meaning one hemisphere bakes in eternal daylight while the other remains in permanent night. Between them is a narrow twilight zone, a band where temperatures might be just right for life. Winds rage, clouds swirl, and weather reaches extremes, yet these worlds show that habitability can take astonishing forms. Then there are the hot Jupiters, massive gas giants orbiting so closely to their stars that their atmospheres boil away into space. Some complete a year in mere days, skimming the stellar surface with temperatures exceeding 2,000 degrees. Their immense size and blistering orbits made them some of the first exoplanets we discovered, and yet their mysteries continue to challenge everything we know about planets and stars. How do such colossal planets end up skimming so close to their stars? Did they form in place, or were they nudged inward over eons by the invisible hands of gravity? Some leave behind glowing trails of gas, like cosmic comets. Others slowly shrink as their atmospheres evaporate under relentless stellar heat. These worlds are unstable, dramatic, fleeting, brief flashes of planetary fire tracing silent paths around distant suns. Not all planets shine in reflected light. Some are astonishingly dark, absorbing nearly everything that falls upon them, darker than paint, darker than ash, darker even than charcoal. One such world, Tres 2b, orbits a star roughly 700 light-years away, reflecting less than 1% of the starlight it receives. Scientists are still unraveling the mystery. Perhaps vaporized metals or exotic compounds cloak its upper atmosphere. The result is mesmerizing, a planet almost invisible, glowing faintly with its own heat, a perfect shadow drifting quietly in space. Some planets wander alone, untethered to any star. These rogue planets drift through the galaxy, expelled from their systems by gravitational chaos or born in isolation like failed stars. Dark, cold, and elusive, they reveal themselves only through faint thermal signatures captured by powerful infrared telescopes. Some may retain internal heat, nurturing hidden oceans for billions of years. Others float entirely frozen, silent and eternal, a planet without sunrise or sky. And yet the question lingers, could life endure in such stillness? On some worlds, clouds shimmer with precious minerals. Imagine skies not of water vapor, but of ruby red, sapphire blue, and titanium-hued clouds, formed when extreme heat vaporizes rocks and lifts them into the atmosphere. On scorching gas giants like Pat 7b, high-altitude mineral clouds drift and swirl, scattering sunlight in strange, beautiful patterns. Picture a world enveloped in storms, bathed in heat, with skies glinting like a sea of jewels above the blazing sun, a spectacle that defies imagination, yet exists somewhere in the universe. The universe is far stranger and more beautiful than we often imagine. Some planets, called super-Earths, are rocky worlds larger than Earth but smaller than Neptune. They may have stronger gravity, thicker atmospheres, and stable climates that could make them surprisingly hospitable. Take K2-44-2b, a rocky planet orbiting in the habitable zone of its star. It receives just the right amount of sunlight, has enough mass to hold an atmosphere, and may sustain liquid water. These worlds could feature deep oceans, steady surfaces, and calmer tectonic activity, all conditions that might allow life to emerge and endure. While we don't yet know if life exists there, super-Earths remind us that Earth is remarkable but not necessarily unique. Some planets move at dizzying speeds. While Earth takes a year to orbit the Sun, certain exoplanets circle their stars in just hours.
Kepler 78b, only slightly larger than Earth, completes a full orbit in 8.5 hours, skimming so close to its star that molten rock likely covers its surface. These ultra-short period planets are often tidally locked, their days and nights frozen in place while gravity stretches and tugs at their very structure. They are extreme, fast, and scorching, tracing sparks around distant suns. Other planets move at the opposite extreme. PSC-B, a distant gas giant, takes nearly 1,000 years to complete a single orbit. Its path is a slow, silent journey, barely held by the star's gravity. Some regions of these worlds may be frozen in darkness, lit only by distant starlight, while their seasons unfold across generations rather than years. On these planets, time moves in a rhythm far beyond human experience. Humanity has now discovered thousands of worlds beyond our solar system. For centuries, we knew only our own planetary neighborhood, the sun, the moon, and wandering stars drifting across the sky. That changed in the 1990s when the first exoplanets were confirmed. Telescopes like Kepler and TESS have since revealed thousands more, some small and rocky, others massive and strange. Some orbit their stars in mere days, others take centuries. Each discovery stretches our imagination and reshapes what we thought possible, and this is only the beginning. Our galaxy alone may contain hundreds of billions of planets, more planets than stars. Each quietly orbits in the dark, unseen yet measurable, waiting for us to detect its presence through the faint shadows it casts. Even if we can never visit most of them, they inspire awe, curiosity, and a sense of wonder about what else might exist in the vast, silent expanse of space. The light from a distant star is usually steady, a gentle glow across the void. But sometimes, for just a fleeting moment, it dims, a tiny flicker. That subtle dip can signal the presence of a planet passing in front of it. This is known as the transit method, one of our most powerful tools for discovering exoplanets. When a planet crosses its star from our perspective, it casts a delicate shadow, barely noticeable. Often less than 1% of the starlight fades. Yet from these faint silhouettes, we can measure the planet's size, its orbit, and even glimpse hints of its atmosphere. It is as if we are watching a distant sun blink, revealing the presence of worlds we cannot see directly. Planets also leave traces through their gravitational pull. As a planet orbits, it tugs on its star, causing it to wobble ever so slightly. This tiny motion stretches and compresses the starlight, detectable through spectroscopy, which breaks the light into its components. Known as the radial velocity method, this technique revealed the first exoplanets and continues to uncover massive worlds, closely orbiting stars or tracing long, silent paths across the cosmos. Here, we are not seeing the planets themselves, but sensing their invisible influence, a cosmic dance written in light. Some planets are losing their very atmospheres. Winds sweep across their skies, clouds drift, and in extreme cases, the upper layers of gas escape into space, like breath dissolving into the void. This is especially true for hot Jupiters, gas giants scorched by their nearby stars. Intense radiation heats their outer layers until hydrogen and helium drift away, forming long comet-like tails. Over time, these planets may lose much of their mass, sometimes leaving only rocky cores behind. These processes reveal how stars shape, sculpt, and even erase the worlds that orbit them. Planetary systems can be even more intricate. Some stars do not travel alone. They orbit together in pairs, trios, or even larger clusters. And around some of these multi-star systems, planets persist. Imagine a sky where darkness never truly comes, where shadows stretch in many directions and one sun rises as another sets. Some planets circle closely around twin stars, while others trace wide orbits around the entire cluster, following paths so delicate that stability is almost miraculous. Seasons would be unpredictable, light constantly shifting, yet these worlds exist, defying what we once thought possible. Some planets orbit the remnants of dead stars, glowing embers or the quiet remains of stellar fury. In some cases, they survived supernovae, enduring the chaos of a star's violent death. Others may have formed from the debris left behind, rising from cosmic ashes into something entirely new. The light from these stars is faint, cold, or distorted, yet their planets continue tracing silent, solemn paths through a kind of stellar graveyard. Some are bathed in radiation, while others drift peacefully in eternal twilight. It is haunting, beautiful, and a reminder that even after an ending, the universe can give birth to worlds both strange and resilient. Not all planets follow the rules. Most orbit in the same direction their star spins, a natural outcome of a solar system forming from a swirling disk of gas and dust. But at least one exoplanet, WASP-17b, defies convention, orbiting its star in reverse. Instead of moving with the star's rotation, it pushes against it. This unusual path likely formed through chaos, a near collision, a gravitational nudge, or some violent cosmic reshuffling long ago. Massive, swollen, and blisteringly hot, this planet completes its orbit every few days. Its backward motion challenges our understanding of planetary evolution, revealing the universe's flexibility, chaos, and endless surprises. Some worlds follow the flow, others push against it, moving through the cosmos with quiet defiance.
Clouds also exist on worlds light years away. Though we cannot see them directly, their presence is detectable as starlight passes through a planet's atmosphere during transit. Some wavelengths are absorbed, others scatter, leaving a delicate fingerprint of gases, molecules, and particles. The results suggest clouds, sometimes dark, metallic, or mineral-based, composed of silicates, iron, or other exotic compounds. These clouds can reflect, absorb, or block starlight, shaping a planet's appearance and temperature. Some worlds are permanently shrouded, others display shifting weather patterns across their skies. From across the void, we can read their weather, just from the way light bends and filters. Some exoplanets orbit closer to their stars than Mercury does. Mercury itself is scorching, stripped bare by our sun. Yet some planets circle so near their stars that nothing in our solar system could survive the heat. They complete orbits in hours or days. Their surfaces may be molten, their atmospheres torn away by stellar winds. Some are tidally locked, one hemisphere trapped in unending daylight, the other frozen in eternal darkness. Others are stretched into teardrop shapes by their star's immense gravity. These extreme worlds defy ideas of habitability, yet their tight orbits make them easier to detect, explaining why many of the first discovered exoplanets were in this category. They are fiery, unstable, and extraordinary, revealing the universe's ability to push planets to extremes. Some planets orbit so close to their stars that the heat is not just intense, it is destructive. Stellar radiation and winds strip away their atmospheres, layer by layer, creating glowing tails of gas stretching like cosmic comets. Over time, these planets shrink, thin, or transform entirely. K2141b, for example, may be gradually losing its surface material with every orbit, slowly eroding under relentless stellar light. These are not static worlds. They are dynamic systems, shaped and reshaped by their environments.
Even planets, vast and massive, can be worn away by the unyielding energy of a star.
The universe consistently surprises us with the unexpected. We have found planets where the skies shimmer with vaporized metals, rocky surfaces hotter than molten lava, gas giants colder than interstellar space. Some orbit backward, tilt strangely, or carry rings so enormous they could obscure a star. Others defy density norms, appearing either impossibly dense or unnaturally fluffy. Some shouldn't exist according to our models, yet they do. Each discovery challenges our understanding of planetary formation, evolution, and possibility. Science thrives on these anomalies, reminding us that the cosmos is as full of exceptions as it is of rules, quiet puzzles scattered across the void, waiting to be noticed. Some exoplanets may be entirely covered in oceans with no land in sight. Imagine a planet with endless liquid water stretching without continents, islands, or shores. These water worlds are not like Earth's shallow seas. Their oceans could be hundreds or even thousands of miles deep. Beneath the waves, pressure would crush water into exotic ice forms and reshape rock into unfamiliar structures. Some might host thick steam-rich atmospheres or hazy cloud layers warmed by internal heat or distant sunlight. If life exists there, it would adapt to currents, chemistry, and darkness rather than sunlight, a wholly alien form of habitability. Earth may be only one version of a habitable world. These deep oceans suggest there may be many others. Not every planet fits neatly into known categories. Between Earth and Neptune lies a diverse group called mini-Neptunes, worlds larger than Earth but smaller than our ice giants, often swathed in thick gaseous envelopes. These planets likely harbor rocky or icy cores beneath layers of hydrogen, helium, and other gases, creating worlds that blur the line between terrestrial and gaseous planets. They remind us that planetary systems are endlessly varied, and that each new discovery expands the boundaries of what we thought was possible. From a distance, these planets might look like Neptune, but inside they can be completely different worlds. Some hide deep, churning oceans beneath thick clouds, while others may lack a solid surface entirely. Too small to be true gas giants, yet too large to be considered rocky super-Earths, these planets occupy a curious middle ground. For decades, astronomers weren't even sure if such worlds could exist. Today, we know they are surprisingly common, possibly the most frequent type of planet in our galaxy. Strange, swollen, and still enigmatic, they fill the space between our expectations and the universe's imagination. Some exoplanets are so inflated that they appear almost weightless despite their enormous size. These puffy planets have low density, making them huge yet soft. If somehow placed in water, they might float like cosmic balloons. Take WASP 17b, for example, a gas giant twice the size of Jupiter, but with a fraction of its mass. Formed far from their stars, many of these planets later migrate inward, where intense stellar heat inflates their atmospheres. Radiation can even break apart molecules, adding to their unusual characteristics. Some display faint trailing tails of escaping gas. Others are so light for their size they defy intuition. They remind us that planets are not rigid, fixed spheres. They can be soft, stretched, and reshaped by the light of their stars. On some worlds, a single day may last longer than an entire year. Unlike Earth, where we rotate once every 24 hours while orbiting the Sun in 365 days, these planets can rotate so slowly that one complete spin takes longer than one orbit around their star. Often tidally locked, they present one face to eternal daylight, while the other remains in permanent darkness, frozen and still. No sunrises, no sunsets, just an unbroken divide between light and shadow. On such planets, even the concept of time begins to blur. A
A day that never ends, a year that rushes past, a sky split forever in two. Some exoplanets are enveloped in thick, hazy skies that obscure the surface below. While we often imagine alien worlds with pristine, clear skies, many planets may be wrapped in layers of murky haze composed of complex hydrocarbons, photochemical smog, or exotic clouds unlike anything on Earth. This effect is reminiscent of Saturn's moon Titan, where a golden fog hides the surface from view. Around distant stars, especially cooler ones, ultraviolet light can trigger strange chemical reactions in the upper atmosphere, creating dense, heat-trapping layers that scatter sunlight and reshape the planet's appearance. These hazy worlds remind us that alien skies may be as mysterious as the planets themselves.
From space, some exoplanets may appear muted or featureless, their colors softened by thick hazes. But beneath those clouds, alien worlds may be alive with motion, oceans churning, winds screaming, and landscapes waiting in quiet mystery. We can't yet see these hidden realms in detail, but the haze hints at worlds cloaked in secrecy, veiled from distant observers. On many gas giants, winds reach astonishing speeds far beyond anything on Earth, especially on tidally locked planets where one side always faces its star. Intense, unrelenting heat drives ferocious atmospheric currents. Observations from space telescopes suggest winds exceeding 5,000 miles per hour, fast enough to cross the United States in under an hour. These winds can shift clouds, carry vaporized metals, and even redistribute the brightest regions of a planet, creating subtle shifts in its glow. Though invisible to our eyes, the motion of these alien skies is written in light itself. Not all planetary heat comes from a star. Some exoplanets are warmed from within. Eccentric orbits or gravitational interactions with nearby bodies can flex and stretch a planet's interior, producing friction and heat, a process called tidal heating. This can melt rock into magma or maintain subsurface oceans beneath icy shells. On such worlds, activity thrives without sunlight, energy pulses from below, and the planet hums with hidden motion. We've also found planets orbiting ancient stars, remnants from the galaxy's earliest days. Some of these systems are over 11 billion years old, with small rocky planets surviving billions of years longer than Earth has existed. They were forged when heavy elements were scarce, formed from materials very different from our own world. Perhaps their surfaces are smoothed by eons of impacts, or maybe life once flickered there long before it arose on Earth. These planets are cosmic elders, resilient, enduring, quietly circling their stars across the deep past. Exomoons, moons orbiting planets beyond our solar system, remain elusive but intriguing. Tiny variations in a planet's transit hint at their presence. One candidate, potentially orbiting Kepler 1625b, could be larger than any moon in our solar system, though smaller moons are likely far more common. These natural satellites could stabilize climates, drive tides, or harbor subsurface oceans like Europa or Enceladus. For massive gas giants, entire moon systems may exist, miniature solar systems in their own right. Imagine a giant planet dozens of times more massive than Jupiter, surrounded by hundreds of moons, each orbiting in silent cosmic harmony. Some moons may be rocky and cratered, while others could harbor icy shells or dense atmospheres. A few might even orbit within the habitable zone of their parent planet, shielded from harmful stellar radiation and warmed by tidal forces.
While we haven't confirmed any of these exomoon systems yet, the possibilities are staggering. Imagine entire families of worlds drifting together, bound in gravitational harmony, far from the warmth of their stars. Life on exoplanets might exist in forms unlike anything on Earth. We tend to picture alien life with blue skies, oceans, and mild temperatures, but some worlds may host life in extreme conditions: acidic clouds, ice-covered oceans, or high-pressure methane-rich atmospheres. Life might not require water, carbon, or DNA at all. On Earth, extremophiles thrive in boiling acid pools, radioactive caves, and sunlight-free volcanic vents. Across the galaxy, microbial networks, chemical colonies, or self-replicating systems could persist in environments humans would find deadly. If we listen closely, through the subtle fingerprints in starlight, we may one day detect a faint signature of life. Some planets exist on the threshold between planets and stars. Known as brown dwarfs or super-Jupiters, these massive objects can fuse small amounts of deuterium in their cores, but lack the energy to sustain true stellar fusion. They glow faintly with residual heat, sometimes emitting infrared radiation. One candidate, HD 10046b, may straddle the boundary between planet and failed star. Where exactly a planet becomes a star remains uncertain, highlighting that the lines we draw in space are often blurred. The cosmos is full of objects that challenge our definitions, existing in the quiet zones between familiar categories.
Many exoplanets lie at the edges of their stars' habitable zones, the so-called Goldilocks zones, where temperatures allow liquid water. Too far, and water freezes. Too close, and it boils away. On these boundary worlds, conditions can vary dramatically. A dense atmosphere may trap heat, reflective surfaces may keep a planet cool, or orbital eccentricities may create extreme seasonal swings. One hemisphere might be habitable, while the other remains frozen or scorched. Life, if it exists here, could survive only in deep oceans, hidden caves, or volcanic vents. These edge worlds are neither fully hospitable nor entirely barren. They exist in a delicate tension, balancing light and dark, warmth and cold. Thanks to advanced instruments like the James Webb Space Telescope, we can now study the atmospheres of exoplanets light years away. When a planet passes in front of its star, starlight filters through its atmosphere, carrying subtle fingerprints of molecules. By analyzing these spectral lines, scientists can detect water vapor, carbon dioxide, methane, and other compounds, and even infer clouds, pressure, and temperature. In some cases, we may spot biosignatures, chemical hints that life may influence a planet's atmosphere. Each spectrum is like a message from across the galaxy, bringing us closer to understanding the true nature of alien skies. Seasons on exoplanets can be far more extreme than on Earth. A larger axial tilt, elongated orbit, or multiple stars can produce summers lasting decades and winters spanning entire lifetimes. A planet might swing close to its star, warming dramatically, then drift far away into frozen hibernation. Chaotic seasonal cycles could allow life to flourish only briefly before vanishing under prolonged cold, or generations could rise and fall within a single summer. On these worlds, the passage of time is measured not in days or years, but in the slow, sweeping arcs of cosmic rhythms, creating calendars written by stars themselves.
On some exoplanets, time itself may seem to flow differently, and so might everything else. Certain worlds exist in perpetual twilight, where day never fully arrives and night never completely falls. This often happens on tidally locked planets, where one hemisphere faces the star constantly, while the other remains in eternal darkness. Between these extremes lies a narrow region called the terminator, a ring of soft, slanted light caught between burning day and endless night. Temperatures here could be relatively stable, winds gentler, and if life exists, it might thrive in this delicate band of muted warmth. There are no sunrises or sunsets, only a horizon fixed in half-light, a world where time drifts in quiet shadow and nothing ever truly sleeps. Some planetary systems display an elegant cosmic choreography. Planets can orbit in perfect harmony with one another, a phenomenon known as orbital resonance. In these systems, the timing of their orbits aligns in simple ratios. For every 2 orbits one planet completes, another completes 3. This gravitational dance stabilizes their motions, preventing collisions over millions of years. While we see this among Jupiter's moons in our own solar system, some exoplanetary systems form extended chains of resonance involving 3, 4, or even more worlds. Each planet follows its rhythm, separate yet in harmony, a delicate symphony of motion. Minor changes in gravity could disrupt the balance, but instead, these systems endure, orbit after orbit, revealing the universe's hidden musicality. Not all exoplanetary observations are immediately understood. Some worlds display irregular light patterns, curves that dim and brighten in unexpected ways, defying simple models. These variations can indicate rings, clouds, or orbiting debris, casting uneven shadows. One famous case, known as Tabby's star, dimmed in mysterious and unpredictable patterns, sparking speculation across the globe. Some suggested swarms of comets, others imagined artificial megastructures, though no evidence supports such ideas. The mystery persists. Light curves wobble, transit patterns shift, and extra dips appear before or after expected planetary passes. Some exoplanets seem wrapped in shifting clouds or trailing dust, leaving subtle but tantalizing clues of worlds still beyond our full understanding.
We are only beginning to unravel these cosmic patterns. For now, they remain unanswered questions, gentle flickers of something beyond our understanding, impossible to look away from. Some exoplanets travel on orbits so extreme that they nearly escape their stars. While most planets trace quiet, predictable loops, others swing in elongated paths, hurtling far from their suns before plunging back like cosmic comets. These journeys can span hundreds of years. At the farthest point, the planet may bask in near total darkness and frigid cold. At the closest, it races past its star, heated in sudden, blinding bursts. These orbits are violent, unpredictable, and often temporary. Some may have been flung into such paths by collisions or close encounters with other stars, and others might one day break free entirely, wandering alone through the galaxy. They are cosmic exiles, dancing at the edge of gravity, each orbit a reminder of the dramatic and dynamic life a planet can lead. Some exoplanets orbit the remnants of dead stars, white dwarfs. When a star like our Sun dies, it leaves behind a dense ember, no longer fusing hydrogen but glowing faintly for billions of years. Around some of these stellar corpses, planets persist. Some survived the star's violent expansion into a red giant and its eventual collapse. Others may have coalesced later from leftover debris.
The environment is extreme, crushing gravity, intense radiation, but life's potential for endurance is evident. Some of these planets may even orbit in narrow regions where conditions could allow liquid water. These worlds circling the dead are anything but lifeless. They are survivors, echoes of resilience, proof that planetary stories continue long after their stars fade. Other planets arise from chaos and destruction. In young solar systems, collisions are common. Planets shatter, moons break apart, debris scatters. From these fragments, new worlds can form, rebuilt from the pieces of what once existed. Observations of dusty disks around stars reveal gaps and rings that hint at ongoing collisions or planetary construction. Some exoplanets may be stripped remnants of larger worlds, others assembled gradually from fragments held together by gravity and time. Scarred, molten, tilted, or eccentric, these recycled planets show that destruction is not the end. It can be the beginning of something strange, resilient, and entirely new. Some exoplanets may have even switched homes. While planets typically form around a single star, over cosmic timescales, gravitational encounters or chaotic stellar clusters can eject them from one system and capture them into another. These interstellar adoptees may follow odd, tilted, or unstable orbits. Tracing their origin is challenging, but chemical fingerprints and unusual motions sometimes reveal their alien past. They are travelers across the galaxy, planetary nomads that remind us the universe is far more fluid and interconnected than it first appears. They are cosmic immigrants, drawn from one stellar family into another, survivors of gravitational drift and chance encounters. They remind us that solar systems are not isolated. They evolve, exchange parts, and occasionally welcome strangers from across the stars. Some exoplanets may resemble the young Earth. Gazing at distant worlds is sometimes like looking into our own past. Certain planets may mirror Earth billions of years ago, when the atmosphere was thick with carbon dioxide and methane, and life, if it existed, was only beginning. Continents may still be forming, volcanic activity reshaping the surface, and storms raging across silent oceans. These distant worlds offer glimpses into the processes that shaped our home, snapshots of an early chapter in the story of habitability, echoes of a planet before life had a name. Not all stars are massive and radiant. Most in our galaxy are red dwarfs, small, faint, and long-lived. Yet around these modest stars, astronomers have discovered giant planets, some as large as Jupiter, orbiting stars barely a tenth the size of the Sun. These enormous worlds often hug their stars tightly, completing an orbit in mere days. The contrast is striking, a massive planet looming over a dim, ember-like star. These pairings challenge our assumptions about planet formation, proving that even small stars can host dramatic, beautiful systems.
Some stars host dozens of planets. While our solar system has 8, other stars may boast 5, 6, 7, or more worlds packed into tight orbits closer than Mercury is to the Sun. In these systems, planets could appear as bright disks in the sky of a neighboring world, orbiting in delicate resonance like gears in a cosmic machine. These compact systems defy our sense of scale, revealing that planetary arrangements can be far more intricate than we once imagined. At the opposite extreme, some stars host only a single, solitary planet. Whether formed alone or left alone after siblings were lost, these worlds orbit in silence. Some are massive gas giants tracing slow, wide arcs. Others are small rocky planets clinging tightly to their stars. The skies of such worlds feel vast and empty. No nearby companions, no gravitational harmonies shaping seasons, just one planet and one sun moving steadily through the dark. There is a quiet beauty here, a solitary rhythm in the cosmic expanse.
Some exoplanets may be veiled in thick, swirling steam. These are not clouds like Earth's soft, cottony layers, but dense, hot vapor, perhaps composed almost entirely of water. Extreme heat can boil oceans, sending plumes into the atmosphere to form layers of opaque, roiling steam. Beneath this shroud, the surface may be hidden entirely, a world lost in mist, a planet both alien and mesmerizing. These steam worlds often orbit perilously close to their stars, where surface temperatures soar and water cannot remain liquid. The result is a planet shrouded in dense fog, its surface invisible beneath rolling clouds. From space, they may appear featureless, glowing faintly through the mist. Beneath that haze, the interior could be a maelstrom of pressure, heat, and chemical reactions. Some may still harbor liquid water deep below, or even rocky surfaces far beneath the vaporous canopy. On these worlds, atmosphere and ocean blur together, and the boundary between sky and surface disappears into mist. Other planets are frozen in ways Earth cannot imagine, where ice behaves more like rock. On our world, ice is fragile and melts easily, but on distant exoplanets, especially those far from their stars or buried under thick atmospheres, ice can crystallize into exotic, high-pressure forms. Dense, solid, and heavy, ices such as Ice 7 or Ice X remain unyielding even under extreme conditions. They may lie beneath thick oceans or deep inside icy super-Earths, forming layers that behave more like bedrock than frozen water. Glaciers may flow slowly under their own weight or stand motionless for eons. Mountains of solid ice may rise unmelted while liquid oceans churn silently beneath miles of frozen crystalline crust. Ice is not all water. On some of the coldest worlds, substances like ammonia, methane, or nitrogen can freeze, coating the surface with frost in pale blues, pinks, or yellows. These exotic ices may form smooth plains, jagged ridges, or glittering fields under a faint, distant sun. Some slowly sublimate, feeding thin, transient atmospheres. Others remain stable for billions of years. Such planets may resemble Pluto or Neptune's moons, but on a grander scale. Massive frozen worlds where chemistry sculpts the landscape, the light is faint, and the air thin and strange. In their stillness, these icy travelers are among the oldest and most enduring objects in the galaxy. Planets also form in the crowded nurseries where stars are born. Most stars ignite in clusters, with hundreds or thousands bursting to life within vast clouds of gas. For a long time, scientists wondered if planets could survive in these chaotic environments. Gravity, radiation, and close encounters with other stars seemed likely to prevent it. Yet planets do exist here. Some cling tightly to their stars amidst ultraviolet flares from nearby suns. Others are ejected early, becoming rogue wanderers. Those that remain witness skies crowded with stars, brighter and more numerous than anything seen from Earth. Even in these bustling, dangerous neighborhoods, planets endure, forming in spite of the chaos.
Some exoplanets have emerged in environments far stranger than once imagined. Early expectations assumed orderly solar systems, rocky inner worlds, gas giants farther out, gentle orbits, quiet stars. Reality proved far more inventive. Some planets orbit 2 or even 3 suns. Others circle pulsars, spinning remnants of exploded stars. Some form in metal-poor regions where theory predicted planet formation was unlikely. Yet in every case, nature found a way. Planet formation is resilient, opportunistic, and patient. Wherever there is dust, gravity works, pulling, clumping, colliding, and shaping new worlds.
Even in sparse outer reaches around faint, unstable, or overcrowded stars, planets appear. Perfect conditions are not required, just time, material, and the quiet persistence of gravity. We've detected planets around stars that are mere millions of years old. Stars live for billions of years, but planet formation can begin almost immediately after a star ignites. In several cases, we've found planets orbiting cosmic infants, still wrapped in the remnants of their birth clouds. These young stars are volatile, surrounded by disks of gas and dust. Within those disks, planets begin to grow. Dust grains stick together, clumps become rocks, and rocks eventually become worlds. Some of these newborn planets glow with leftover heat. Others are still pulling in material, growing larger day by day. Their orbits shift. Their atmospheres are not yet stable, but they are real, worlds in progress, taking shape under the light of a very young sun. They remind us that planet formation is not just theory, it is a process we can witness in real time. Other planetary systems are far older than Earth itself. Our planet formed around 4.5 billion years ago, but some exoplanetary systems have existed for 10 or even 11 billion years. Their worlds have survived galactic mergers, stellar outbursts, and billions of orbits without being destroyed. One such system, Kepler-44, hosts 5 small rocky planets. Its star is more than twice as old as the Sun, yet its planets circle steadily, silent witnesses to the galaxy's ancient history. These time capsules, remnants from the early universe, hold clues about the first planetary systems formed when heavy elements were scarce. If life arose there, it could be unimaginably ancient. In such a galaxy, we are newcomers, arriving in a realm already filled with quiet, enduring worlds. Some exoplanets are measured in tens of Jupiters, massive beyond imagination. These giants blur the line between planet and brown dwarf, too small to ignite fusion and become stars, but far larger than typical planets. Often orbiting far from their stars, they glow faintly with retained heat. Some have dense cores, while others are almost entirely hydrogen and helium, with atmospheres thousands of miles thick. Their gravity is immense, their weather systems sprawling across hemispheres. Any moons orbiting them could themselves be large enough to support life. These are the heavyweights of the planetary family, slow-burning, colossal, quietly unique. Not failed stars, not oversized planets, something else entirely. Other worlds are dense enough to crush iron. Planets come in every size and density imaginable. Some are so light they could float in water. Others are compact, their interiors pressed together by unimaginable forces. We've found rocky exoplanets with densities twice that of Earth or more. Their surfaces might look familiar, solid, cratered, mountainous, but beneath, pressure rises dramatically. Iron may exist in exotic forms, cores may be enormous, gravity intense, and rotation rapid despite their mass. Walking on such a planet would feel strange. The ground beneath your feet is heavier, more unyielding than anything on Earth. These are not gentle spheres. They are iron-rich mysteries, compressed by gravity into worlds both alien and extraordinary. We've found planets so lightweight they could float in water. In contrast to dense, iron-rich worlds, some exoplanets are astonishingly fluffy, low-density gas giants with vast diameters but surprisingly little mass. Saturn is the least dense planet in our solar system, yet some exoplanets go even further. With densities lower than wood, they are made almost entirely of gas. If you could find an ocean big enough, they would float. These puffy planets often orbit close to their stars, where heat causes their atmospheres to swell dramatically. Beneath their vast, transparent skies, small, dense cores may hide. Clouds drift slowly, winds meander, and the worlds themselves feel almost like bubbles, delicate giants held together by the gentlest pull of gravity and gas.
Other planets have lost their atmospheres long ago. A planet's air is fragile. Over billions of years, solar winds, radiation, and violent impacts can strip it away entirely. Some rocky exoplanets, especially those near their stars, may once have had thick atmospheres, now reduced to nothing. Spectral fingerprints reveal the evidence: faint absorption, barely a trace of gas, leaving bare rock and lifeless plains. These planetary ghosts, stripped to their cores, circle in silence, reminders that even worlds can be weathered and hollowed by time. Yet some planets are still actively gaining mass from their disks. Planet formation is not instantaneous. Around young stars, swirling disks of gas and dust can linger for millions of years, feeding growing planets. Some still pull in gas, dust, and rock as they orbit, glowing in infrared light from their leftover heat. Spiral patterns, gaps carved by gravity, and bright clumps of material reveal worlds still taking shape. These baby planets are hot, unstable, and unfinished. Watching them is witnessing creation in real time. We have even observed planetary destruction. Planets are often thought permanent, yet some vanish before our eyes. Kepler's space telescope detected a small rocky world dimming and flickering, shedding mass in a dusty tail as it orbited its star. In another system, a sudden flare of infrared light hinted at a massive collision, one planet colliding with another. These events are not theory, they are reality. Creation and destruction play out side by side in the quiet machinery of the cosmos. Some exoplanets might even be covered in metallic snow. On Earth, snow is light, soft, and familiar, but on certain hot gas giants, snow may form from metals such as titanium or iron. High in the atmosphere, these metals condense into droplets, solidifying into crystalline snow. Aluminum oxide could create clouds high above, leading to mineral snow reminiscent of sapphires falling silently through alien skies. These flakes may never touch the surface, vaporizing on the way down, drifting in a shimmering dance shaped not by water, but by heat, pressure, and exotic chemistry. And some planets are trapped in intricate gravitational dances. Planetary systems are not always chaotic, some are choreographed. Exoplanets can become locked in precise interlocking orbits, moving in rhythm with their neighbors. Each orbit complements the others, a cosmic ballet of stability and timing, where even the smallest gravitational tug contributes to the harmony. These patterns are called mean motion resonances. For example, one planet may complete exactly 2 orbits for every 3 of another. These aren't random arrangements. Over millions of years, gravity gently nudges planets into these repeating paths, creating a stable rhythm. Resonances can prevent collisions, stabilize orbits, and allow many planets to exist close together. Systems like TRAPPIST-1, with 7 rocky planets orbiting a small star, show this harmony in action. It's as if the planets are keeping time, a quiet cosmic clockwork moving together in rhythm. These dances may last billions of years, their balance preserved long after we are gone. But not all systems are harmonious. Some appear unstable, their planets teetering on the edge of chaos. Gravitational simulations suggest that over tens or hundreds of millions of years, these systems could unravel. Planets might be ejected, spiral into their stars, or collide catastrophically.
What we see now may be a snapshot of a system slowly collapsing, a spinning top that hasn't yet tipped. Even the universe has fragile arrangements where gravity's delicate work may one day fail, and the planets, for all their size and silence, are not immune. Some exoplanets have extremely tilted orbits. Most orbit roughly in the plane of their star's disk, but others are skewed, sometimes at extreme angles, even perpendicular to the star's equator. Such tilts often arise from gravitational interactions, close encounters, or ancient collisions. A planet born in the ordinary plane can later be flung into a steep orbit. Tilt affects climate, seasons, and orbital stability. From afar, we only see the current path, but the lean of the orbit tells a story, a history of motion, disruption, and cosmic upheaval.
Some planets spin backward. Most planets rotate in the same direction they orbit their stars, but a few exhibit retrograde rotation. Their spin is opposite their orbit, likely caused by dramatic events, collisions, tidal interactions, or strong gravitational encounters. Sunrises and sunsets on such a world would happen in reverse. Weather patterns swirled the wrong way, and the sky itself would feel subtly off. These planets are rare, but real, rebels slowly spinning against the flow of their stars. We've even measured winds raging across alien worlds. Even without seeing them directly, we can detect movement in their atmospheres. On some gas giants, winds blow at over 500 miles per hour, fast enough to cross a continent in under an hour. Tidally locked planets, where one side always faces the star, experience extreme temperature differences, driving massive jet streams. Heat from the day side rushes toward the night side, and storms circle endlessly, carrying vaporized metals or exotic clouds across the globe. We can't feel these winds, we can't hear them, but through subtle shifts in starlight, we can sense their motion, a whisper of weather from a world light years away. Some exoplanets are bombarded by intense stellar flares. Not all stars are gentle. Young red dwarfs in particular can erupt with sudden bursts of radiation, thousands of times stronger than anything our sun produces. Planets orbiting close to these stars are caught in the storm. Their atmospheres can be stripped, molecule by molecule, by ultraviolet and X-ray radiation. Magnetic fields may offer some protection, but without them, the surface could be scarred or rendered uninhabitable. Stars like Proxima Centauri flare dramatically, raising questions about whether life could survive in such a tempest or whether atmospheres could ever recover. On these flare-battered worlds, habitability depends not just on distance from the star, but on the star's temperament itself. Yet some planets bask in the calm glow of quiet red dwarfs. Not all red dwarfs are violent. Some burn steadily for trillions of years, emitting gentle, unchanging light. Around these stars, planets may orbit close enough to receive warmth without being battered by flares. They may be tidally locked, one side in eternal day, the other in endless night, yet a band of twilight at the terminator could offer mild temperatures and a potential refuge for life. These are some of the most promising cradles for long-lived ecosystems, worlds illuminated by a ruby-colored sun, slowly turning beneath a patient, tranquil sky. Some exoplanets are wrapped in auroras that never end. On Earth, auroras shimmer near the poles, caused by charged particles interacting with our magnetic field. On distant worlds, these lights can be immense, stretching across hemispheres or encircling the planet in continuous bands. Tidally locked planets may blaze with starlight on one side, while their night side glows with electric auroras. Gas giants with strong magnetic fields may exhibit arcs of green, blue, or violet shimmering visibly from space. These are skies alive with light, shaped not just by air, but by the invisible energy of their stars.
Some of the hottest exoplanets harbor clouds of vaporized rock. On these scorched worlds, minerals like silicates and aluminum oxide can evaporate, rise as gas, and condense into suspended clouds. These clouds absorb and scatter light in strange ways, creating metallic storms or skies tinged yellow, gray, or blood red. Winds can carry sand like dust at supersonic speeds. Here, the sky is not made of water, it is made of rock, ground to mist, drifting high above the surface, forming alien weather systems sculpted by heat and gravity. Some planets are slowly falling into their stars. Close-in worlds can experience shrinking orbits over millions of years due to tidal forces and gravitational interactions. Their descent is silent but inevitable. We can detect planets with decaying orbits, their periods shortening imperceptibly with each revolution. Though the skies may remain bright and days may pass normally, above them, gravity steadily pulls, counting down the time until they are consumed in a final flare of light and heat. At the opposite extreme, some planets are flung outward into interstellar space. In chaotic early systems, close encounters with giant planets can give smaller worlds enough velocity to escape entirely, becoming rogue planets. These solitary wanderers drift through the galaxy, cold, dark, and starless. Some are Jupiter-sized, others may be Earth-like but frozen solid. Yet even without a sun, internal heat may persist, quietly sustaining a hidden pulse beneath frozen surfaces.
From fiery storms to eternal auroras, from falling worlds to wandering exiles, exoplanets reveal the astonishing diversity of planetary life in our galaxy. The cosmos is alive with motion, energy, and change. These are not static spheres, they are dynamic worlds, sculpted by light, gravity, and time, each with a story waiting to be discovered. Some exoplanets host subsurface oceans warmed by radioactive decay. These are the ultimate wanderers, cast out, unbound, yet still planets in every sense. Silent drifters carrying secrets we may never hear, worlds adrift in the dark, glowing faintly with hidden heat beneath their frozen crusts. Others have orbits that stretch across entire systems, while most planets circle close to their stars, maintaining a delicate balance of light, warmth, and gravity. Some follow paths so vast they loop through their systems on centuries-long journeys. Their orbits are elongated, elliptical, or nearly unbound, taking them from the blazing heat of a star to the freezing edges of space. Some lie hundreds of astronomical units away, where their suns are little more than faint points of light. These distant voyagers drift along edges of gravity, tracing arcs as slow and majestic as time itself. Between extremes, some planets exist in cosmic Goldilocks zones, not too hot, not too cold. Here, temperatures allow liquid water to persist, the key ingredient for life as we know it. Earth sits in this zone, as do an increasing number of exoplanets. But being in the Goldilocks zone is no guarantee of habitability. Atmosphere, rotation, and surface conditions all matter. Still, these planets are among our best candidates for life, whether rocky, ocean-covered, or clouds-wrapped. They lie in the same delicate sweet spot that cradles our world, bathed in gentle starlight, balanced on the edge of possibility. Some exoplanets might have Earth-like temperatures. Planets like Kepler 442b and TOI 700d orbit quietly, receiving just the right amount of starlight to prevent freezing or boiling. Their equilibrium temperatures hint at the possibility of water, moderate climates, and perhaps even familiar weather.
We cannot yet see their surfaces, but we can imagine standing beneath skies that might feel strangely familiar. Winds stirring oceans, clouds gathering at twilight, rain falling gently across distant plains. Yet many worlds boast entirely alien weather. Weather is shaped by a planet's chemistry, atmosphere, and energy balance, and on some exoplanets, these factors produce phenomena unimaginable on Earth. Clouds of molten metal, rain of molten glass, or liquid methane streaking across the sky. Winds roared at tens of thousands of miles per hour. On frigid planets, ammonia snow drifts across frozen plains. On scorching worlds, silica dust swirls in the air, painting the sky red, yellow, or black. Lightning can flash through vaporized rock, and storms may rage for centuries. These are not gentle climates. They are extreme, violent, beautiful, and utterly alien. Across the galaxy, planets reveal the full range of possibility, from drifting icy wanderers to long-orbiting giants, from temperate worlds that whisper of life to planets with weather sculpted in fire and metal. Each planet, each orbit, each storm is a story, a reminder that the cosmos is vast, strange, and endlessly inventive. Some planets may have permanent jet streams that never shift, steady winds circling their worlds in endless motion. Others experience sudden planet-wide weather events triggered by stellar flares, storms that erupt without warning, reshaping the climate in hours. These are not Earth-like climates, they are weather systems forged from unfamiliar physics, beautiful, terrifying, and quietly unimaginable. Other worlds are shaped by ice volcanoes and subsurface oceans. Not all geological activity is fiery. On icy exoplanets, volcanoes may erupt not with molten rock, but with slushy mixtures of water, ammonia, or methane. These cryovolcanoes, seen on moons like Enceladus and Triton, likely exist far beyond our solar system as well. They spew cold liquids into the sky, which freeze and settle back down. Beneath the surface, hidden oceans remain warm, insulated by thick layers of ice, sealed for billions of years. In the silence of these frozen worlds, water flows like rock, cracks open, ice moves slowly, and something stirs deep below, an ocean dreaming beneath a still, frozen world.
Some planets lie in the quietest corners of the galaxy. The Milky Way is full of motion, stars orbiting the center, clouds collapsing into new suns, planets spinning through space. Yet in the galactic suburbs, far from crowded centers and spiral arms, stars move slowly in solitude. Planets orbit here under dim, steady starlight, free from tidal disruptions or stellar encounters. They trace stable paths for billions of years. Time moves slowly here, giving life, if it exists, a chance to evolve, adapt, and endure. Cold and distant, these worlds offer a rare cosmic shelter, a quiet haven in the vastness. Others speed through chaotic, crowded starfields. Some planets form in dense regions near the galactic bulge, spiral arms, or globular clusters, where stars crowd together. Orbits shift, gravity nudges worlds off course. Planets may collide or be captured by passing stars. Here, the night sky is a constant shimmer of dozens of suns, moving and bright. Yet amid the chaos, planets endure, circling their stars like dancers in a packed, ever-shifting ballroom of light and fire. Some planets orbit pulsars, the remnants of massive stars that exploded in supernovae. Pulsars are dense, rapidly spinning neutron stars, beaming light like cosmic lighthouses.
No one expected planets to survive such violent births, yet astonishingly, some do. In fact, the first confirmed exoplanets were discovered around the pulsar PSR 1257+12. These planets orbit a star long dead, pulsing dozens of times per second. They may be survivors of an ancient system or newborns formed from fallback material circling the pulsar. Either way, they are among the strangest worlds known, silent companions to a collapsed core, orbiting a star that no longer shines with fusion, yet still casts its ghostly pulse across the galaxy. These are planets around the dead, reminders that life, motion, and worlds can persist in the shadows of stellar death. Ghost worlds orbiting ghosts. Some planets may have survived the explosions of nearby supernovae. Supernovae are among the most powerful events in the universe, brilliant, violent stellar deaths that can outshine entire galaxies for a fleeting moment. Most things nearby are destroyed, yet some exoplanets endure. If a star in a binary system explodes, the surviving companion and its planets might remain, scorched but still circling. In other cases, planets may form later from the debris. Astronomers have found heavy elements like iron and calcium in the atmospheres of certain white dwarfs, a subtle fingerprint of planets that once orbited them, and perhaps still do. Any world that survived such a blast would carry the imprint of catastrophe, a scorched surface, an atmosphere forever altered, yet still existing, a planet that witnessed a star's final breath, a silent survivor of cosmic death. Some worlds have atmospheres rich in exotic gases. Earth's air is familiar, mostly nitrogen, a touch of oxygen, water vapor, and carbon dioxide. But exoplanets can be far stranger. Some are filled with hydrogen and helium like gas giants. Others host methane, carbon monoxide, or thick clouds of sulfur compounds. One planet, HD 209458b, shows signs of escaping hydrogen, its atmosphere drifting off into space. Another carries titanium oxide in its skies. These gases define everything: temperature, color, weather, and the light reflected from the planet. Some atmospheres are transparent and searing, others are murky, choking, and metallic. Air, it turns out, is not always soft, blue, or breathable. Sometimes it burns. Some planets may be carbon-rich or oxygen-poor. On Earth, oxygen dominates biology. Elsewhere, carbon may reign. These so-called carbon planets could harbor mountains of graphite or diamond, oceans of hydrocarbons, and skies filled with methane instead of water vapor. Others may have iron-rich surfaces and carbon-based clouds, worlds where life, if it exists, would follow entirely different rules. The elements themselves tell a new story, a version of a planet written in chemistry unfamiliar to us. Not every world resembles Earth, yet each is a real place, a home to alien chemistry and exotic possibilities. We are beginning to search for biosignatures, clues that life might exist across light years. On Earth, oxygen, methane, and water vapor appear in ratios that hint at life. Now, astronomers look for similar patterns on distant exoplanets, splitting starlight into spectra to detect fingerprints of biology. It is delicate work. Clouds, temperature, and stellar type all influence the readings. Already, some planets show water vapor, others suspicious carbon compounds. The next decades will probe deeper for ozone, chlorophyll-like markers, or chemical imbalances that hint at life. We have not yet found life, but we are listening more carefully than ever, watching for the faintest flicker in the cosmic dark.
Some exoplanets are swept by dust storms that never end. On Earth, dust storms are fleeting. Elsewhere, they may rage for years or decades, blowing across barren landscapes and lifting particles into endless swirling clouds. On such worlds, the sun fades behind a copper or brown haze, features vanish beneath drifting grit, and the planet may appear smooth and featureless from space. These are worlds shaped by wind and dust, harsh, beautiful, and endlessly moving, a testament to the power of alien weather. These dust storms affect temperature, light, and even atmospheric chemistry. They may shape a planet's climate entirely. Any life there, if it exists, would not adapt to rain or snow, but to an endless hush of dust, stirred by slow, relentless winds that sweep across barren landscapes year after year. Some planets, in contrast, shine like beacons, while some worlds hide in darkness, muted and almost invisible. Others reflect enormous amounts of starlight. This can come from highly reflective clouds, smooth icy surfaces, or even exotic metal-rich layers. Kepler 7b, for example, may be cloaked in silicate clouds that gleam like polished stone. Some planets act as cosmic mirrors, glowing with borrowed light, visible across hundreds of light years. Their reflectivity, or albedo, can be so high that they outshine their stars in certain wavelengths, not by producing light, but by echoing it. Brighter than Venus, brighter than snow, these worlds remind us that sometimes it is reflection, not heat, that makes a planet luminous. Not all planetary systems are wild or strange. Some resemble scaled-up versions of our own solar system. Small rocky planets circle close to their stars, while larger gas giants orbit farther out, sometimes with icy belts or asteroid zones akin to our Kuiper Belt. These familiar structures suggest that certain laws of planetary formation may be universal. Gravity arranges dust and gas. Rocky worlds form near stars. Gases condense farther out. On a larger scale, these systems echo the rhythm of our own, hinting that Earth may not be so unique. Yet many systems break every rule we thought we knew. Gas giants orbit closer than Mercury. Planets trace tilted, elliptical, or even retrograde paths. Stars may host more planets than we expected. Moons may rival planets in size. Worlds migrate from their birthplaces, reshaping the entire system architecture. These arrangements defy expectations, challenging our models of planetary formation. Perhaps planet formation is not orderly, but wild, creative, and flexible. Each system is a new variation. Each planet tells a different chapter of the same cosmic story. The universe is improvising, building worlds we never imagined. We are now entering an era of direct exoplanet imaging. Until recently, planets were detected indirectly by dimming starlight, slight wobbles, or transits. Now, engineers and scientists are creating powerful telescopes capable of photographing these planets. Using coronagraphs to block starlight or giant star shades to create artificial eclipses, these instruments aim to capture faint dots of planets beside the brilliance of their stars, offering humanity its first real glimpse of alien worlds. From that tiny dot of light, we can extract a world. We can study its atmosphere, measure its chemistry, even search for the faintest signs of life. Telescopes like the Nancy Grace Roman Space Telescope and future missions such as LUVOIR or HABEX aim to do what once seemed impossible: take portraits of alien worlds. Soon, exoplanets will no longer be shadows or subtle signals. They will be places seen with our own eyes. Some planets may already have been photographed in blurry detail.
Using extreme precision and clever techniques, astronomers have directly imaged a few exoplanets, huge gas giants orbiting far from their stars. These images are crude, showing only faint, tiny specks of light, but they are real. We have captured the glow of heat from planets still cooling after formation. We have watched distant gas giants slowly orbit over years, confirming their motion across space. The HR 8799 system was among the first glimpsed this way. These images may lack detail, no continents, no clouds, but they mark a new chapter in astronomy. For the first time, humanity has seen light from a world orbiting another star.
As our instruments improve, so will the images. One day, we may see weather patterns, oceans, or even signs of life. For now, we have a blur, a whisper, a beginning. The search for life often begins with planets. When we imagine life beyond Earth, we picture worlds with air, water, sunlight, and time. So our gaze turns to exoplanets. We look for those in the habitable zone, scanning for oxygen, methane, or other biosignatures. We study their orbits, stars, and atmospheres. Every detection raises questions. Could water exist here? Could microbes survive? Could something live at all? Even the smallest hint, a spectral wobble, a faint adsorption line, sends ripples through the scientific community. If life exists elsewhere, it will likely be on a planet, not in a drifting gas cloud, not in an asteroid belt, but on a distant world that has quietly turned for billions of years, waiting to be noticed. Exoplanets are our mirrors, our windows, the places we search when we wonder not only whether life exists, but what other stories the universe might be telling. Every new discovery reminds us how strange the universe can be. We expected Earth-like planets. Instead, we found lava worlds, rogue wanderers, planets with icy rings, molten skies, and tightly packed systems. We found planets orbiting dead stars, worlds where weather, chemistry, and gravity dance in ways we never imagined. Every new system adds a twist, a shape, a possibility. The universe is not just big, it is inventive, playful, endlessly creative. And the thousands of exoplanets we found are likely just a tiny fraction of what exists. For centuries, humans imagined planets as rare companions scattered sparsely among the stars. But today, the evidence is clear. Planets are everywhere. The average star likely hosts at least one planet. Many host several. There may be more planets than stars in the Milky Way. Hundreds of billions of worlds, giant, small, hot, frozen, familiar, and utterly alien. These numbers tell us something remarkable. Planetary systems are not exceptions, they are the norm. The galaxy is not just a field of stars, it is a vast garden of worlds, each following its own path, each a story waiting to be told. Somewhere among billions of stars, worlds like Earth may be waiting, blue, warm, alive, or quietly beginning. We don't know where, we don't know what they look like, but they exist somewhere in the vastness. Each discovery brings us closer to finding these distant twins, reminding us that we are not alone. Tonight, we've drifted through strange skies, frozen oceans, blazing deserts, and alien storms. We've glimpsed planets flung into darkness, wandering far from their stars, and worlds shaped by fire, ice, and time itself. Every planet we've imagined or seen is a story, a quiet gravity well in the sea of stars, a question waiting in silence. And even now, as you rest, the cosmos continues. Stars shine, planets turn, and somewhere in a distant sky, a world not unlike our own spins slowly through its night. You are already part of this universe, already floating, already home. Rest now.
The planets will keep turning, the stars will keep shining, and the universe will wait. Good night.